Thank you. Thank you very much for this invitation. So today I will talk about hydrofluctuations in a class of many-body systems called linear degenerate systems. So I will give you the definition of linear degeneracy in a moment. But these systems are basically the kind of systems that behave much like integrable systems at the hydrodynamic scale. So naturally, integrable systems are the kind of very special example of such linear degenerate systems, but they don't have to be integrable in general. So they are kind of halfway between integrable systems and non-integrable systems in a sense. So in this recent paper with Giga, we provided a general recipe to characterize hydrodynamic fluctuations in such linear degenerate systems. But in this talk, just for clarity, I will focus on a certain class of linear degenerate systems called stochastic charged cellular automata. So these are very simple models that allow you to analyze many aspects of the systems, including dynamics. So these systems have been worked out fully microscopically by people, including Giga. And recently, we tried to also apply some hydrodynamic ideas to describe the dynamics in these systems. So these systems are good because they are kind of nice linear degenerate systems, but there is also another kind of motivation for us to study the fluctuations in these systems. So these stochastic charged cellular automata are known to show a kind of very intriguing phenomenon called anomalous fluctuations. And originally, I think it was discovered in the context of spin transport in the Heisenberg chain. But later on, it was discovered that these models, charge, so these systems conserve charge, some kind of charge, theta charge. And it was discovered that the charge current statistics in these systems look much like what you used to see in the spin current statistics in the easy access Heisenberg chain. And so people started to also study the current statistics in these systems in order to have some intuition about anomalous fluctuations. Anyway, I don't really talk much about anomalous fluctuations. I just wanted to say that there are some good reasons to study the dynamics in these systems. Okay, so right. I guess many of you are already familiar with these the notion of current fluctuations, but just to set the stage, let me start with some basics. So the kind of situation I'm considering is the following. I'm just an example. So suppose your system's in some statistical ensemble, like an equilibrium or local equilibrium. And then what you want to do is to count the number of particles that pass a certain position in your system, for example, the origin. And for some given period of times, let's say large T here, like here. And every time you make such a measurement, you get a slightly different number because, as I said, the system is in some statistical ensemble. So the number you get, the transferred particle, number of transferred particles would be changing for every measurement. But the way these numbers fluctuate is not going to be completely arbitrary, but it's going to fluctuate around some mean value. So the mean number of the transferred particles. And the actual kind of fluctuation around the mean value is controlled by the certain probability distribution, which I call current fluctuations. In the context of mesoscopic systems, it's also called, the study of current fluctuation is also called full counting statistics. So that's what I'm interested in here, and that's what I mean by current fluctuations. There are many, well, not too many, but there are some tools that people have been using in analyzing such current fluctuations. For example, for certain solvable systems, there is a very powerful tool called integrable probability to really exactly characterize current fluctuations. This kind of approach can be used to, for example, stochastic exclusion processes like SEP and ASEP. And it's quite powerful and sophisticated mathematically, but at least to my knowledge, it's not quite generic in the sense that it can't be, for example, used to characterize current fluctuations in Hamiltonian systems. There are also other kind of approaches that are more general in the sense that they can indeed be used to characterize current fluctuations in other models like Hamiltonian systems. For example, we have a theory called Macroscopic Fluctuation Theory, and more recently we devised a kind of extension of MFT to describe current fluctuations in ballistic MFT. So there are some tools that you can use to study current fluctuations. Experimentally, people also have looked into current fluctuations quite some time in different contexts. For example, I guess in 90s, lots of experiments were done to study the flow counting statistics of electron transport in macroscopic systems like quantum dot systems. More recently, people studied current fluctuations in more generic Hamiltonian systems like 2D magnets using some experimental setup called quantum simulators like superconducting qubits and optical lattice and etc. So these simulators really allow you to have a good, precise control over the ultra cold atoms, and you can really probe the statistics in these mesoscopic systems. So these are the kind of current status about the study of current fluctuations. So let me start with some, so before jumping to linear degenerate systems, I just wanted to quickly remind you of how current fluctuations in diffusive systems can be understood, because I guess these systems are probably more intuitively clear to you. So for simplicity, let's consider a very simple system with just one conservation law that diffuses the system, like non-integrable spin chains, if you like, which conserve just the energy. So for these systems, you can analyze the hydrodynamics using linear fluctuating hydrodynamics. So the large-scale dynamics of these systems is captured by the hydrodynamic equation like this. So because the dynamics is diffusive here, you have to rescale the coordinates like this, like that, yes. And then you have this Fick's law here, and then this is the white noise in the system, whose strength is controlled by the Osnaga coefficient, which is just the product of the diffusion constant and the susceptibility. So for these systems, what people know is that usually, unless the system is made of non-interacting Brownian motions, the typical, current fluctuations, typical current fluctuations, which are characterized by the way the variance of the current scales are going to be given by this. So it's going to, this variance is going to scale like the root of t. And the current is going to have a Gaussian probability distribution. The typical current fluctuation is going to have Gaussian probability distribution. For example, in CEP, so it's a very simple exclusion process. It's been known that the variance is going to be given by in the way that I just mentioned, and this coefficient is also explicitly known. Oh yes.
But so maybe a dumb question, but this linear fluctuating hydrodynamics, is this something you can derive, or is it a commonly accepted assumption about how the macroscopic behavior should be?
Yeah, that's a good question. I guess for very simple systems like CEP, you can probably, okay, I'm not it's not like I can give you some different on top of my head, but I think people derived, correct me if someone knows that's not done, please correct me, but I think it was done. Basically, I think for these systems, you can derive this kind of fluctuating hydro. But yes, for generic systems, I do not think that's possible, certainly not for Hamiltonian systems. But there are good reasons to argue that this is true. Fick's law usually describes diffusive behaviors at large scale, and also there has to be this kind of white noise in order to describe some kind of fast modes that are not usually incorporated in in hydrodynamics, which are for slow modes. So this is a very common kind of equation used for characterizing diffusive motion at hydrodynamic scale in this system. Yeah. Okay, so that's something people have known for some time. So I just mentioned these typical fluctuations, but you can also consider large fluctuations. So what I mean by that is you can also ask what would be the kind of probability distribution for the current when it fluctuates on a different scale, meaning when the current is fluctuating on this order with this scale. In this case, the large deviation is, large deviation principle is going to give you the answer. So the probability distribution for the current that goes like this is going to be given by this relation, where the phi is given by the large deviation function, like this. And this is also related to another quantity called scaled cumulative generating function by Legendre transformation. And this is something I guess people more frequently compute because it's easier to compute, I believe. So for example, for SEP, we know that this is going to, its kind of generating function is going to behave like this at large T. And then this Fm lambda is known exactly like this. I guess originally it was computed by Derrida and Leibovitz in this paper using the kind of elementary version of the technique of integrable probability. And then later on, people confirmed that the MFT can also give the same result fairly recently by Kiron and Tomohiro. And somewhat interestingly, this kind of SEP-like behavior was also found in U1 charge conserving random quantum circuits recently. So it seems like, SEP is a very simple kind of go-to example of diffusive systems, but this kind of behavior seems to be very universally found in other systems as well. Anyway, so this is something people have known for some time, but what I want to focus on in this talk is slightly different. So linear degenerate systems having the ballistic transport as the most, as the largest kind of hydrodynamic behavior in the system, which is to say that the most relevant kind of a leading contribution to its hydrodynamic behavior is coming from the ballistic component in the equation. So the Euler equation is the leading hydro equation for linear degenerate systems. And you have this A matrix here, which is called flux Jacobian. It's just a derivative of the current with respect to the density. It can be also written as in this form in terms of normal modes, and this is often more useful to work with. This is just a nonlinear transformation. So this is the hydro equation for linear degenerate systems. And what makes it linear degenerate then is the following property. So if the system is linear degenerate, the velocity of every mode has to should not depend on the normal mode itself. So this relation, this equals 0, has to be true for every conservation law in the system. And this also automatically means that the so-called G matrix, which appears in nonlinear fluctuating hydro, is 0 for every component, meaning that there is no self-interaction in the system. And this automatically implies that there's no superdiffusion in linear degenerate systems because of the absence of self-interaction. Well, at least superdiffusion cannot happen according to, the kind of superdiffusion prescribed by nonlinear fluctuating hydro wouldn't happen. It wouldn't rule out any other mechanism by which superdiffusion happens, but at least generically it wouldn't happen. So this means that the subballistic contribution to this Euler equation in these systems would be diffusive, not super diffusive. But what is interesting about this system is that there are two sources of diffusion, namely normal and convective diffusion. So the normal diffusion is the usual kind of diffusion you also had in SEP, for example, like this. Whereas convective fusion is a kind of very unique contribution to these systems. And this can be intuitively understood by invoking a certain kind of special case of these systems called, namely, integrable systems. Integrable systems are the kind of special case of linear degenerate systems. So in these systems, only convective fusion contributes as the source of diffusion. And this is simply because in these systems, you basically have a bunch of quasi-particles that elastically scatter. And because of these elastic scatterings, the initial diffusive fluctuations in the system, so the fluctuations in the initial condition, can be really carried all the way to some, to some finite time dynamics you're looking at without losing the strength. So the diffusive fluctuations in the initial condition basically can be also, transported according to the Euler equation in these systems, and they contribute as a diffusion at later times. So that's why in integral systems you have this kind of convective diffusion, and the similar kind of situation also happens in linear degenerate systems, although these systems are no longer integrable in general. So that's why we have the coexistence of these two sources of diffusion in linear degenerate systems, right? Okay, so that's the kind of quick definition of linear degenerate systems. But from here on, let me focus on the concrete example, which we call stochastic charge cellular automata. So these cellular automata are very simple lattice model, 1D lattice model, which is defined as follows. So every state in this automata can be given by either the vacancy or the negative charge or the positive charge. There are three possible states at every site. And by enumerating all these states, at every site you have the full state at given time t. And then the question is, how are you going to update these states at given time? The way you do that is to apply this two-body map, this kind of two-body map in a brickwork way. So this is the kind of circuit architecture. And every two-body map acting on two neighboring sites is going to update two neighboring sites in the following way. So if the two neighboring sites have vacancies, then nothing happens. If one side has a vacancy and neighboring side has some non-trivial charge, then they're going to swap. And lastly, when there are two differing charges on the neighboring sides, then with the probability gamma, they're going to swap. And with the probability 1 minus gamma, they remain at the same position. So meaning that when the gamma is 0, actually the system has an exclusion interaction. And this is a very useful deterministic limit, which people often take. And I'm going to also take that limit occasionally. And with this two-body map, you can have this full dynamics like this. And that's the dynamics, basically, of the system. And this has been solved microscopically, as I mentioned earlier. And and they are known to show anomalous fluctuations.
Sorry, just a question. So if the charges are equal, they don't evolve at all?
No.
Right.
Yes. All right. Yes. So what I want to do here is the hydrodynamics. So in order to do that, I have to know the thermodynamics of the system. So these systems are known to be having an exponentially large number of local constant charges because of this very simple structure. But as it turns out, the most relevant, there are actually only three physical charges in these systems, namely the total charge here, and the so-called left and right movers. So the right moving particles, for example, if you look at this kind of diagram, is obviously conserved. This diagonal, the number of particles that go like this along this right light cone is clearly conserved. And likewise, the number of left moving particles is also conserved. So, and the total charge is by the definition conserved. So there are three conservation laws. And for these conservation laws, you can do the hydrodynamics. And the reason why, I mean, okay, you might then say that, well, in principle, there are also other charges, and dynamics of other charges might also influence the dynamics of these three physical charges. But that's a reasonable question. And for generic initial conditions, I suppose that's the case. But what we want to do here is to initialize your system by preparing the initial GGE with only these charges. And if you initialize your system with these three charges, we can show that at least at the hydrodynamic level, the dynamics is closed in the sense that these three charges time evolve by just referring to each other's dynamics and not knowing the dynamics of other higher conserved charges. That's why we can just focus only on these three charges. And for example, for the GG averages of these densities, of the left and right movers, and also the total charge can be given in this way, although it's not quite, I mean, you don't have to remember these now. All right. Now, so as I said, I want to do the hydrodynamics, and for these three charges, you can write down three Euler hydrodynamic equations like this. So this can be obtained by evaluating this A matrix, flux Jacobian like this, which you can do because I mean, you can do this for this model because we know the microscopic structure of the system. And as you can see, this is linearly degenerate because, okay, the dynamics of the left and right movers is trivial, right? It's just going propagating along the light cone. The dynamics of the total charge is a bit more complicated, but again, it's linearly degenerate because the velocity of the charge doesn't depend on the charge itself. It depends only on the densities of the left and right movers. So that's why this is a linear degenerate systems, and this properties was also sometimes called charge inertness. But in practice, it's easier to work with the normal modes. So okay, these are already normal modes, so you can just transform this equation into that equation in terms of normal mode. And indeed, this B appeared already. So B field here is just a hyperbolic tangent of beta C. And the beta C is the chemical potential associated to the total charge. Okay, so so the normal mode can be defined like this. And so you have basically three different velocities in the system, the +1, -1, corresponding to the left and right movers, and also some non-trivial velocity V here, like this. And this V is going to be zero basically in equilibrium, meaning when the rho plus equals rho minus, this is just zero, and it's going to be important for its own dynamics. I mean, the presence of such zero velocity. Anyway, so this kind of equation has been actually also observed already in the context of so-called Dirac fluid. So this kind of system also has three-component Euler hydro, which really looks like this. Okay, so as I said, in equilibrium, the velocity kind of vanishes, meaning that okay, it doesn't automatically mean this, but you can sort of realize that when the system is away from half-filling, the dynamics is basically ballistic because this A matrix is non-trivial. Whereas when the system is at half-filling, at charge neutrality, then you can basically see that this A matrix is going to vanish. I mean, it's not, yeah, I mean, these two parts vanish, and then around the equilibrium, this V also vanishes. So basically the charge, the ballistic contribution to the charge transport vanishes. And this doesn't automatically mean that this is the sub-ballistic contribution to this system is diffusive, but I mean, macroscopically, one can kind of show that this is diffusive.
Is integrability relevant to this discussion?
Integrability is relevant, yes, in the sense that this linear degeneracy is very much intimately related to integrability.
But I thought you only used like 3 charges.
That is correct. Yes, so technically I don't use integrability, but the fact that these 3 charges have this linear degeneracy is related to integrability.
I understand. Thank you.
No.
Sorry, actually a related question. I thought that your charges should, these beta i's, right? You have only 3 chemical potentials, but in a GGE, I presume that there is one, conserved thing corresponding to every tracer particle. Isn't that
So
right?
which particle, sorry?
Every particle, so because there are more conserved charges than just 3, right?
Well, yes, that's precisely the case here. But what I'm saying is, so my initial condition is spanned by only 3 charges. And in that case, so there are no other higher beta i's, if you like. And in that case, the dynamics is going to be self-contained, closed in the sense that this kind of dynamics is closed. The dynamics of other charges wouldn't enter into this dynamics. That's why you can forget about these 3 other charges, so long as your initial condition is given only by these 3 charges. That's what I mean by.
Yes.
Yeah. You have to do some kind of nonlinear transformation, which I didn't write explicitly, but you can do that. Yeah. Okay. So for large, okay, let me start with large fluctuations. Although my focus will be on typical fluctuations. So as I said, large deviation is given by this large deviation principle like this. And the object of interest here is the so-called scaled commutating function, like defined in this way. So we want to compute this basically. And importantly, here the cumulants defined in this way cannot be obtained by just taking the higher derivatives of this f of lambda and evaluating at lambda equals 0. Usually you can do this, but because of essentially because of anomalous fluctuations, you can't quite get these cumulants in this model. And I will show that in a few slides. All right. So to calculate this f from lambda, you can of course try to do it macroscopically, which Jiga and others did. But instead, the approach we want to take here is to use BMFT basically, so ballistic macroscopic fluctuation theory. So this is a kind of a hydrodynamic fluctuation theory that relies only on the hydrodynamics. So the important idea here is that there's no dynamic generated fluctuations in these systems. So you can, the kind of fluctuations you have to sort of, evaluate at later times can be fully characterized by the initial fluctuations by just transporting or propagating the initial fluctuations using the Euler equation. And that's the kind of underlying idea in the BMFT. So the idea it can be implemented as follows. So you start with the fluctuating hydrodynamic density fields. So this is with hat, this is the microscopic density, but because I'm looking at the ballistic scale, you have to rescale the coordinates like this, and you define this rho I. And notice that this is still fluctuating. It's before evaluating its average. So this is still a fluctuating variable. And then, as I said, you have to propagate the initial condition. So you have to initialize your initial fluctuations properly. And this is done in this way. So the initial density distribution is given in this large deviation fashion, where f of rho is known to take this form. It's a very simple exercise, and you can work it out. Here, f is just the free energy density. And And finally, this the density, sorry, the fluctuating hydrodynamic density has to be transported by the hydrodynamic equation itself, the Euler equation, and this can be accounted for by imposing this kind of dynamical constraint using delta function. And here, I just exponentiated this delta function in this way. And by combining all these, what you can do is to write down this kind of path integral for the generating function. So this path integral is given just in terms of the density here, density fields, fluctuating density fields, which I defined here. And then you just insert this the exponential of the total charge current, the initial fluctuation, and then the propagation of the initial fluctuation via the Euler equation. That's it. And then you can just show that this whole thing in here can be neatly put in this form, where this is having this form where it's where the action is appearing in this way, and it's multiplied by this large parameter tau. So this is very welcoming, because you don't have to work and evaluate this path integral explicitly, but you can really just take the Sadhu point here, so long as you're interested in the large tau limit. So this path integral is dominated by the Sadhu point of the action, and this leads to the set of VMGT equations like this. I wrote this down for generic systems, but and that's why you have all these indices. But for the stochastic charge to the automata, this looks more. This looks simpler. And then you can just try to solve these VMT equations and by plugging the solutions to this expression, you can compute FM lambda. And I wouldn't bore you with the technical detail. I just give you the final result. So you can solve this equation for the charge to the automata. And this is the final result, FM lambda, which is exactly the same as what was same as the microscopic result obtained in this paper. And you can now very easily appreciate that this IFM lambda is a bit problematic in the sense that, if you try to calculate the cumulant by taking higher derivatives of it, they are going to be divergent in time. So that's why, well, this model, I mean, this is basically a reflection of the anomalous fluctuations. And the reason why this kind of behavior happens is intuitively clear. It's basically because of the presence of the normal mode that now propagates with the zero velocity, meaning propagates along the ray here. And because whenever you have such a normal mode with a zero velocity here, the cumulants evaluated along this ray and cannot really have a usual exponential clustering. And that's why the current cumulants evaluated along this ray have to decay algebraically. And that's why this FM lambda now has this kind of divergence. So there is a proliferation of fluctuations along this ray because of the presence of the normal mode. But this doesn't happen in anharmonic chains, for example, because there's no self-coupling. All right, now I want to move on to the typical fluctuation. So the scale of the typical fluctuation is set by this dynamical exponent here. And then for this, again, I want to evaluate the generating function here. And eventually what I want to do is to compute this kind of probability distribution for this rescaled current. And I define the typical probability distribution like this, and this is what I'm going to compute. And this is usually having a Gaussian distribution for generic systems. But as we will see, they're not quite, that's not quite the case for these systems. So the task now is to evaluate this typical probability distribution. But this is not, it's not always easy. But here we kind of claim that we can again use the idea based on BMFT, meaning that in linear degenerate systems, again, fluctuations are even typical fluctuations are given by just the initial fluctuations, because essentially there's no dynamic generated fluctuations in these systems. So we can just again propagate the initial fluctuations using the Euler hydrodynamic equation, and then try to evaluate typical fluctuations at later times. And that's what I'm going to do here. So for simplicity, I'm going to take this deterministic limit. So it's something called single file limit. And then later on, I will move on to the more generic case. So for this case, you can say that now, because we are probing the typical fluctuation, you have to rescale the coordinates like this, and then it's going to be Gaussian distributed because it's an initial condition, right? So the density field is now fluctuating like this, where delta rho is now, yes, given, I mean, it's delta correlated like this with the susceptibility controlling its strength. So that's the initial, this is the initial condition. And now by applying this formalism to our models, the cellular automata, you can do the following. So the dynamic exponent is now known to be 2. It's diffusive. So you have to rescale the coordinates like this. And then you initialize your initial fluctuations like this, okay? Now you have to then propagate the initial fluctuations using the hydrodynamic equation or the hydro equations. For left and right movers, it's very easy. It's just, again, propagating on light cones. And you can solve that explicitly like this. For the charge transport, it's less, it's more complicated, but you can still solve this using the method of characteristics. And in the end, you wind up with this kind of expression for the fluctuation of the charge density. So xd of t here is given by this kind of a characteristic equation. So you have this. So this is the characteristic line. And in terms of this, you can now show that the total charge current on the typical scale is given by this expression. So you just have to plug everything again, like we did for the large fluctuations in this path integral formula. So now it's given by just the initial density field, as opposed to the density fields evaluated at arbitrary space and time. And the integrand is like this. And the nice thing is that, as I said, this is given by just by initial fluctuation. So you can actually evaluate this integral explicitly. So I will just skip the details here, and then you can trust me that in the end you end up with this kind of expression for the generating function. So you can really, there's no assumption actually here, and you can just go from here to there, at least for these models, okay? And then if you use that and plug that into this definition, then you realize that the probability distribution at the typical scale is given in this non-Gaussian form. It's actually a skewed kind of distribution. And you can also show that, okay, this is for the half-filling case, but away from the half-filling, you can also play the same game, and then you can actually see that the contributing fluctuating fields are actually different. So for this case, the initial charge fluctuation is a solo contribution to this anomalous typical fluctuations. Okay, so that's what we saw last year, but there's another kind of more recent result, which is going beyond this previous single file limit case. So in this case, now we have this generic gamma. So the dynamics is fully stochastic. In this case, as I said, you have not only the diffusion from the convective diffusion, but also have normal diffusion. So you have to also account for this normal diffusion, which is stemming from the stochasticity in the system. And but you can actually write down a fairly simple, again, fluctuating hydro equation like this. Now, you just have, on top of this diffusion from convection, you have this Fick's law accounting for the normal diffusion. And again, the white noise has to be also put, and where this, the L is the Onsaga coefficient. Okay. Now, importantly, this normal diffusion doesn't influence the dynamics of left and right movers. So this is the change coming from the stochasticity is really, is only this essentially. But this is different still from the linear fluctuating hydro equation I wrote down for the SEP. Because this diffusion constant that appears in the Fick's law is actually not the bare diffusion constant, but it's a projected one, meaning that it has to be projected. I mean, it's a convective contribution has to be projected out like this. And this is necessary because by taking the zero stochasticity limit, you want to reproduce the previous single file limit, right? In order to achieve that, you have to actually have this kind of projected diffusion constant. But we actually also derived this projected diffusion constant. So I'm not just saying that this has to be the case, but we can really show that this is indeed the case from the calculation. And accordingly, also the Onsaga matrix here is the projected one. And then you can just calculate the generating function as before, a bit more involved, but still fairly straightforward. You end up with this kind of expression, which might appear a bit nasty. But again, we confirmed that this agrees with the microscopic result. So you can actually also derive this kind of typical probability distribution, even in the presence of stochasticity, using the technique of integrable probability, as done in this paper. But we confirmed that the hydrodynamic approach can actually also give rise to the same result, which is quite satisfying. And the effect of stochasticity is now to smear out this cusp here, the probability distribution here. In the case of single file limit is having a very sharp structure like this. But by turning on the stochasticity, you can see that this cusp here is going to be a kind of round now. But the cumulants are still diverging in time, so the anomalous fluctuation itself is still present in the system. It's just the cusp is kind of disappearing. All right, so let me conclude. So I just try to demonstrate that the degenerate systems are the kind of peculiar systems whose hydrodynamic fluctuations have not been worked at least to our knowledge. And we provided a recipe for doing that. And I chose this cellular automata as an example. And in these systems, normal and the convective diffusion coexist. So you have to do that properly in order to account for these sources. I used BMFT and BMFT-based approach to characterize both large and typical fluctuations, and they seem to work. So the outlook is how about BMFT for for systems that are not linear degenerate. So these linear degenerate systems are very kind of special kind systems where BMFT can really be used. But in general, if the system is not linear degenerate, you have shocks, and then the BMFT, as it stands now, wouldn't be immediately applicable to such systems with shocks. So you have to, generalize the BMFT. And also another direction that we are pursuing these days is to use this approach to study spin current fluctuations in the Heisenberg chain in the easy access regime, and it seems to work. So that's quite satisfying, and hopefully we can report that reasonably soon. Okay, so let me stop here. Thank you very much.
Questions?
So is it possible to go a bit away from integrability to do all of this?
I mean, the
BMFT
system is non-integrable, right? I mean, so in this cell automata, single file limit is only integrable limit, and in Away from the single file limit, where the gamma is greater than 0, it is.
I guess my question was like, if you start from MFT and then like turn on a little perturbation to make it unintegrable, non-integrable, and can you like see that it matches with the prediction of BMFT?
Oh.
Or maybe it does work like that because you're taking large time limit.
So you start with the BMFT, right? And then turn on the...
Right, that's what I...
Should be possible. I don't think people have done that, but it should be possible.
I see.
So you mentioned that in your system, the most of the fluctuations is coming from the initial state and not from...
No, not just most. I mean,
all in this.
Yeah, for the single file limit, yeah.
Right. So, but in your system, in the lattice model, you still had the exchanges when they hit, there was exchanges, right? So there is indeed stochasticity also coming from the dynamics.
Yes, correct.
So what is the scale? Why is it that the stochasticity coming from the dynamics is subleading as compared to the stochastic?
No. I mean, the stochasticity does give rise to the diffusive behavior, and that's why you have this fixed law, basically, in this case. Whereas in the single file limit, there's no stochastic exchange. It has a single file interaction, meaning exclusion interaction. So it's fully deterministic in the single file limit. So that's why there's no such stochastic.
So I didn't mean this, but in the beginning part where you did the BMFT.
Yeah.
So there you didn't have any stochasticity coming from the dynamics, right?
Yes, for the BMFT, there's no.
So what was the justification there that the stochasticity that comes from the dynamics is subleading?
Okay. So you're talking about BMFT. Yes, because you're looking at basically the ballistic behavior. And the quasi-particles are carrying these ballistic, the motions. And I guess that's the kind of reason I would have for this kind of last expression, not dependent on stochasticity. I mean, usually you'd have kind of, I would assume some kind of dependence on stochasticity. But basically, what is happening here is only these quasi-particles are the carrying initial fluctuations, and they're not dependent on the stochasticity, and they're not, giving rise to this kind of largest scale behavior. But the subleading behavior, which is accounted for in the typical fluctuation, will be influenced by the.
And the last one, is there any other alternative ways of verifying this expression, either by microscopic?
Oh yeah, that's what done in this paper.
The model has been solved microscopically.
It has. I mean, that's prior to our work. So
okay.
Maybe if I can just comment on this last question. I mean, to understand the question was, can you hear me? So to understand the question was, if typical fluctuations are gamma enters into typical fluctuations, why does it not enter into large fluctuations? And the reason for that is that essentially the large fluctuations are set by the larger scale behavior, and both the deterministic and the non-deterministic case have ballistic contributions, and it's those ballistic contributions that drive the large behavior. And you can see this from the macroscopic solution, that the stochastic contribution, the large deviations of the stochastic contribution are square root of t, even on the large scale. But for the deterministic, they are t. So there is a speed difference between the large deviation functions. But on the typical scale, they basically match, because this convective contribution is essentially just a fluctuation of the velocity around 0. And that's also on the square root scale, the same as on this stochastic scattering.
Thank you very much, Takato. And so this approach propagates the statistical fluctuation initial state in time. But if you consider a quantum system at zero temperature, the statistical fluctuations are essentially dying. Instead, you have the quantum fluctuations.
Correct.
Do you think it is possible to generalize these methods to include quantum fluctuation, maybe to have a crossover between the classical and the quantum?
Yeah, I think I've been thinking about it for quite some time, but.
So that was a good question.
Yeah, it is a quick question, but I don't know how to do it for the moment, because we have to make sure the quantum fluctuations are going to scale in a way that can be used for BMFT, right? For example, in this initial fluctuation now, sorry. Yes. So for example, the initial fluctuations, thermal fluctuations are now having this large deviation form. But for quantum fluctuations, I don't know. I mean, would it take this kind of form? Then maybe it might work. I guess it's a technical problem to me. I mean, things have to scale in the correct way so that you can use BMFT and, you know, because otherwise you cannot say that the whole thing would be controlled by saddle point, and that's the whole point here. So
Okay, thank you.
Yeah, maybe I can make a comment on this one. So for free fermions in 1+1 dimensions, you can write the dynamics of the free fermions in terms of the Wigner phase-space distribution. And there is a certain large n limit that you can take where n is the number of particles. Yeah, so n going to infinity and h bar going to 0. In that limit, there is a phase-space hydrodynamics description that comes, which is somewhat similar to this GHD approach.
Right.
And there is a systematic way of finding out the quantum corrections in terms of, you can call it 1/n, or you can call it h bar, which is the same thing because I'm taking n h bar fixed. And so the Euler equation is given in terms of Poisson brackets, and the corrections are given in terms of Moyal brackets. Right. So that's a particular h bar deformation of this. So this, for free fermions at least, it can be done quite exactly. Yeah. Okay, so if there are no further questions, let's thank Takato for an excellent talk.